So welcome to this math reading group on the signature transform, and okay, so some of the things associated with that. We won't be talking too much about like the deep math because to be honest I'm a little bit scared of it, but mostly focusing on the signature transform. So to give you a brief outline, we'll be talking about the basics of the signature transform, mostly taken from the primer paper. That's for the first part, and then for the second part, we'll see how the signature transform is applied, at least in a very recent paper, to show how to exactly quantify the expressive power of, for example, Mamba and other SSMs like it. So at least it's nice because it's a fairly well-developed mathematical theory that gets used to show that okay, this model can approximate this class of function and do this well on it. So I thought the second paper was pretty interesting. Okay, so let's just get in. So a path, it's really nothing much complicated. It's just a function from some closed interval AB to Euclidean space RD. It could be something else, but here we just care about d-dimensional spaces, and really just a bunch of components. So a path xt, notice that here, because the signature comes more from stochastic analysis, they typically use the notation from that theory. So you have x of t with t underscore just mean okay, it's the x at time t, and I have coordinates x1t to x dt for in this case. And so most of the examples here are just okay, functions that are continuous or absolutely continuous, which you might just think as almost everywhere differentiable. Um, but in principle, this can be extended to sort of weaker classes of functions that, such as those we can find in stochastic analysis. So one nice thing of these tools is that they can be applied to very, let's say, a wide variety of sequence or time series analysis problems, especially those where you have a lot of noise. That's not a problem in this case. So, but here we're just talking about differentiable ones. So for example, a path on the left is simply t squared, well, it's simply the graph of t squared on the interval -1 to 1. But I don't always have to have t, just the identity as one of my components. I can just have, for example, on the right, cosine of t, sine of t, and that obviously just draws a circle. So a path is just a curve in some space, and you want to do things with that. Um, we'll see later that really path is just okay. If you have data that comes in some order, let's say you have sampled discretely some space, or you have data that has a sequence to it. Signatures are really the right tool for that. At least if you don't care about the spacing between your points. But anyway, we'll get to that. So one thing you can do with these paths is do something called a path integral. So for example, if I have some function f on the real numbers, that's nice enough, so usually continuous for our purposes, and the path x from a, b to r, I can take the integral of f of xt with respect to d of xt, and okay, in stochastic notation, the d of xt is simply the time derivative of x with respect to t, so dx over dt times dt. So at the end, it's just a single real integral of f of xt multiplied by some other function. So that's very easy. Just compute it or estimate it numerically if you have to, um, and then this is actually just a special example, a special case of the thing on the bottom where if I have two paths, a path y and a path x, I can integrate y against x by simply this formula. So simply the integral of the product of y of t times the time derivative of x over dt. And so that's an integral. I can compute it, and in particular, I can do things with a single path and compute various kinds of these. So a quick example. Um, let's say x is here just the path t squared, and x of t is simply the path t. Really, I should say, shouldn't even have these accolades here. So that means that this dx of t is simply 1 times dt. And so at the end, the integral is just the integral of t squared over dt. That's just t cubed over 3. Uh, then compute the bounds using the of the integration, and you're done. So nothing especially fancy here. You just need to be able to compute integrals. Now, given a path, let's say here in d dimensions, I can compute some specific integrals. So these will form what we will call the signature. And for example, the first term is called, so if index I from a to t, it's simply the integral of the ith component of x respected to t from a to t. And okay, I can also note this down as so instead of having the bounds of the integral as this, I can also just write it this way. It's more useful for later. Okay, this first term is really easy. It's just by the fundamental integral of integration is simply the I, so xi at time t minus xi at time a. So no big deal. But okay, this is now also a path, right? It's a function that takes a time t between 0 or a and b and gives me an output. And so again, I have a path, and so I can do that again. So let's say here I want to integrate with two indices, I and j. Okay, so I sort of define it recursively as the integral of over s from a between a to t of s of xi with respect to dxj. And so that just gives me a double integral of dxi and dxj with the sort of small detail that really I'm not integrating both of them from a to t. I'm integrating s from a to t and integrating r from a to s. So in a sense, my integral is more like of a triangle. What if I first have, let's say this would be t, this would be more s, and this would be r. So I'm not exactly integrating over the all values of combinations of r and s. So one thing that means is that the integral here is not commutative. That's a sort of important distinction. And but doing that means that you get more information about your actual path. So let me finish with this. So okay, we can keep going. Given some k tuple of indices I1 to ik, um, okay, the signature for these indices is simply going to be the iterated integral, in this case for example, with respect to ik of s of I with I1 to ik minus 1. And so it's just a recursive integral, and so at the end it's just, okay, very large and maybe not so nice computing integral, but just integral. So let's say now I take all these possible k tuples of indices with all possible values of k. That gives me an infinite number of values, right? Because each of these boil down to just a number. And so I have an infinite quantity of numbers that describe my path. And it turns out that so this collection, which we call the signature, it contains all the information about the path. So the nice thing about that is that you sort of, it's a bit like the Fourier transform or stuff like that, where you sort of take in a single function and you're describing it as just a stream of values that, if you take all of them, give you all the information you need. So notice that here we take at 1 at the beginning. That's simply for the 0th order integral. We don't take any indices. Um, but yeah, so you can think of it as a bit like the Taylor expansion or the Fourier transform, but in a more very generic sense. Notice that it will come later, but these multi-indices here, I'll call them, okay, the space, the set of all of these, I'll call them WD, where D is the dimension, so the number of indices I get. W for the set of words, of course. Okay, so a small recap. So the signature of the path is just the collection of all iterated integrals of all multi-indices. I can group them also by order. So okay, the constant 1 is just order 0. Then I have d order 1 terms, one for each index, and then I have my pairs of so d squared for all the other terms. So to me, when I first looked at this, it felt a bit, oh, it's a bit like the moments of a probability distribution, where I have multiple parameters. I can, or not exactly multiple parameters, but a multivariate distribution I can characterize in terms of, okay, the mean, then the covariance, and then maybe even some higher order terms, where for a single dimensional distribution is just scalars, but if you have multivariate distribution, then okay, the mean is a vector, the covariance matrix is a matrix, of course, and then beyond you can sort of imagine these like higher order objects, and these are for me tensors, and so we can also think of the signature here as just an element of the tensor algebra on RD, which is like a huge vector space where you have scalars, vectors, matrices, order 3 tensors, order 4, and so on. So all the orders. So if you want to like give a space for this to live in, that would be the one you should choose. But we won't get too much into that. So a first application which needs some context, but it's nice because we sort of catch up on some of the stuff we didn't talk about during ODEs. So suppose you have a first order ODE of the following form. So dy over dt is simply f of yt, and you have an initial condition. Okay, you might want to know, do I have a solution and is it unique? And it turns out that it's very easy to get that, thanks to this process called the Picard theorem, or the Picard iteration. And it begins with, okay, taking this equation and integrating with respect to t, assuming that you have the solution y of t. Okay, now you get that y of t is y of t0, so this y0 plus the integral from t0 to t of f of ys s times ds. So of course this depends on the right hand side term also depends on y, but it's in a sense it defines a fixed point equation. We're saying that y, the function, is equal to some map f applied to y. And so if you take this thing later, okay, I have a fixed point equation. Maybe I can just iterate, like start from a point and apply this map f enough times, and I get closer and closer to the solution. And that's sort of what the Picard theorem says. So define a sequence of functions that are not the solution but like get close. Say yk is simply going to be y of t0 plus the integral of from t0 to c of f of yk times s, so just iterating the fixed point equation with initial condition simply the constant function y0 of t is equal to y0. And then we have the Picard-Lindelof theorem that says that if f is continuous in t and something called Lipschitz continuous in y, so what Lipschitz continuous means is the thing on the right here. So if I have y1 and y2, I need that to have that the distance between f of y1 and f of y2 is smaller than some constant k times the distance of between y1 and y2. You can sort of think of this as saying that the derivative of f in y must be bounded. So if you have these conditions, this sequence yk converges to a fixed point of the fixed point equation. And so that's sort of how you prove that you get a solution for this. And so an example, it takes some calculations to do the full details, but let's say I have the equation dy over dt is equal to y of t, with initial condition y of 0 is equal 1. It turns out that by doing these calculations, the kth term of my sequence here, yk of t, simply the sum from n to 0 of so n to k, sorry, of 1 over n factorial of times t to the power of k, or t to the power n. And you may recognize this as simply the truncated sequence of the exponential function, and so as n goes to, k goes to infinity, sorry, this converges to exponential of t, which is in fact the solution of the equation. And so you can think of this as simply you're building the Taylor approximations of the full solution. So this is good to give you an idea, but the same principle will apply to the signature transform, or at least specific things. So these specific things are called control differential equations. Um, let's say I have the following. So I have first two paths. So a path x from 8b to rd. That's going to be my driving path. You can think of the input or some like external forcing on my system. And I have some map v that takes some vector in re and returns a linear map from RD to RE. And then I'll have my state y was being driven by x in the following, saying that the derivative of y at the time t is v of yt, so that's a linear map applied to dx of t. So that checks out. Um, this is a linear equation, but it's very general. Okay, we'll say that y is a solution of this equation if it satisfies the following equality on the bottom. So it's a fixed point of the map here, so y of t is simply equal to y plus this integral. But here we've replaced it with a path integral instead. And so we can sort of, again, compute them. Okay, the first term is simply constant y, and then I have y plus the integral of vs dxs, which, okay, the paper, at least that's not the primer, but the other one, the foundations one, says this is equal to this. I'm not exactly sure what they mean here, but maybe we can figure this out. But at the end of the day, you get something that looks like a bit like a Taylor expansion, but if you see these terms, right, okay, you have integral from a to t of dv dx, then integral from a to t and a to s, so with so dx dxs. So I guess essentially something that looks like these my path integral or my signature transform terms. And so that's the idea here, is that in fact the full solution is expressed as a combination of the signature transform terms. Okay, so if we take the nth iterate of this sequence, we get this huge sum. So I get y0 plus the integral of the n minus 1 term, and that's simply going to be a big sum of some iterated integrals. So all of these, they depend linearly on signature transform terms, which means if I have the full signature transform, I can just easily compute the solution here. And also, of course, the sequence is going to converge to the true solution in some sense, within some other conditions. So I think the paper mentions that for like continuous path, for smooth paths, it works fine. If you have less than that, you can also do some things. So this theory is a bit more general than what we saw previously with ODEs, because we have an input that drives the equation that might not be super nice, but we don't care. Okay, so before moving on to like applications, one important property of the signature is that it is invariant under time reparameterization. I should drink. It is invariant under time reparameterization. what that means, if I sort of change how the scaling of time in my system, in my path, that doesn't change the signature. So let's say I have two paths x and y, and psi is going to be my like time rescaling, so it needs to be monotonous, continuous, and non-decreasing. So maybe, oop, like maybe this is the standard time, and maybe psi looks like this, right? So this is a time rescaling, which means that the path is going to be the same points, but maybe not at the same time. So what we have here is that actually, so let's say I have my time reparametrized path, so x tilde and y tilde. Okay, so that means that the d of x tilde t is simply dx tilde dx psi tilde times the time derivative of psi. And okay, that means that the path integral of y tilde against dx tilde, I can eventually just rewrite it as the path integral of y against dx. So that's what it means. It does not really matter how time is sampled here. It's only the order in which I visit the point. So it might be unfortunate if you care about that, but for most problems, I think you're pretty happy that you have this property. I can easily, like, because you might have your data that looks like this, and you don't really care about the exact time, you just care about the shape of your path. So having this property is very useful.
I had a question.
Yeah, go ahead.
If the path integral is invariant under the time reparameterization, then sorry, this is from a previous slide, but the linear mapping that gives you the solution to some equation, uh, that one will not be invariant under time reparameterization.
So which one exactly?
That was the slides 12.
So
Uh, yeah, so
you mean the
these repeated
DD one?
integrals, they depend linearly. Yeah.
Um, so here it says that that's the part where the paper does not exactly mention what they mean here, so it might have been a typo. I think we can just think of this. But in the end, um, okay, it's just the integral of some linear map times dx. So it doesn't even matter that it's not really a time reparameterization, because it doesn't need to be to satisfy these conditions here. So I don't think it's the same sort of class of transforms.
Yes. So the fact that it depends linearly means that the exact way it depends linearly should change with the time of consideration.
Um, See, I'm not sure about that, because this here says that my time remapped integral is just equal to the original integral. So so that means that the signature of this path is the same as the signature of this path.
Yes. So not the since signatures are invariant and um, the repeated integrals they are not invariant because they present the solution to the differential equation, then and they depend linearly. That means that whatever linear mapping there is, that thing must vary with the parameterization.
Mhm. I'm not so sure there, because if the signature transform is the same, then it's going to be the same linear map. No?
Yeah, um,
I think here in this case, like if you change the time parameterization, both y and x change at the same time, so it's always the same term that's going to get mapped. It's just at a different time, but otherwise it doesn't really matter. Yeah, the order of the points matter, but the exact time at which it does not. Okay, but maybe we can come back to that. So at least that's a fairly important and useful property. In most cases, I would guess. There might be some application where this is important, but here not. Okay, so before moving on to the second paper, um, let's talk about like the general way you might want to use the signature transform. So let's say you have some discrete time series data, or really anything that comes in a sequence, so x1 through xt. The first step would be construct a continuous path, and you have multiple ways of doing that. So either linear interpolation, rectilinear, so basically piecewise constant, splines if you want to be fancy. They also have the lead lag transform, which is a bit more complicated, and I'm not even sure the paper explains it properly. Whatever you do, you get some continuous path that encodes your data, and now we can compute the signature to that. So of course you cannot compute the full signature, right? You don't have infinite compute, so you truncate it like you would truncate a Taylor expansion. And because of this property that a lot of things we care about, like the signature, you can figure it as a basis for the space of functions of your paths. So that means that if you use them, the signature terms as features, you only really need basically just a linear combination of the signature terms to get any function. So that's the general idea. So then of course, okay, maybe you profit, maybe you don't. Depends on your problem. The paper gave a bunch of examples, but there will be toy ones, so we can look at the paper later, but otherwise let's move on. So the second paper on so theoretical foundations was very interesting because okay, they say actually these state space models and Mamba in particular, we can reframe them as a specific kind of these path differential equations. So let's say I have some path x and some other path u. Here x is going to be my state and u is going to be more my actually no, x is not going to be a state, but I have two paths. U is more the input and x is also something depending on the inputs, but not so clear. So suppose that they are continuous or really differentiable, and let's say I have a differential equation that looks like this, or control differential equation, where so x here is supposed to have channels, so I here is just for each channel, so it's more inspired by how Mamba has per channel equations, so that I have a linear map A applied to Z, Z is my state, um, over dx, and then B times my input, so B is more straightforwardly the input term, and Z is the state in the state space models. So let's say I have this linear control differential equation. Um, we can compute its solution using the signature transform simply as just a sum of over all the indices. So remember, indices are simply the k tuples for all k in n. So any tuple of the indices I might want. So first a sum of a times 0 z 0, so the initial state, and then the signature transform for that multi-index, and then the double sum 1 over each channel, and then again over each multi-index of AI. So it's yeah. So sorry, A of multi-index I, and then B over channel I, and then have an integral over the signature transform. So if you were to look at this, it's basically the same as the basic equations for state space models, like linear state space models we saw the last time. Actually, maybe not last time, but when we saw state space models, right, we had sort of a similar equation. This is just a generalization, but here we can uh, swap in the, the, the signature terms. Okay, so the paper goes on then to show that popular state space models like S4 and Mamba, they fit in that framework. So we can choose X and U appropriately to model S4. So for example, S4, remember the equation, that the discretized equation were like this. So the ZL is simply so A times ZL minus 1 plus B times XL, again over each channel. Um, we can turn that into the following equation if we take x of t being t, so that the dx of t is simply 1, so it doesn't, that's why we don't have any x on the left here, and u of t is simply the integral of my input embedding here. I've put it to y of s, doesn't really matter. We can do the same for Mamba. So Mamba, it's the same equation as above, but now a and b, they depend on the input x. And so specifically the way they depend it is shown on the bottom here. So it's essentially the same as having d of zt is a of zt times dx of t plus b of dot, and then dx of t and dot, they depend on this. So I think it's either dx of t or x of t is simply this term, so a sigma, I think it was a not a softmax. Uh, Surely someone remembers better than me how Mamba worked. Um, just some function that depends on the state. And so the nice thing about this is that, okay, we can describe Mamba, we can describe S4 and some other things like GLA, I think they mentioned, so gated linear attention, so a whole class of models. We can describe them as linear control differential equations. So that means we can use the theory of these controlled differential equations, in this case to show how expressive is Mamba, for example. So let's do that. So this is the one of the main results. Let me have some water. So assume I have again paths x and u. Such so here it's more of a technical requirement. So the first two channels of x are t and t squared. Then linear CDEs of the type we've seen previously, they can approximate any functional of this form. So a continuous function of the path. From the path. So here the notation is a bit maybe weird, but it says absolutely continuous functions from 0 to 1 to dx. The absolutely continuous is the one. You can think of this as just simply differentiable, or yeah, differentiable functions. It's fine. That start at 0. That's one small technicality, is that actually the signature doesn't really depend on the initial points. So if you have a continuous function of the whole path plus the integral of some continuous function of the state along the whole path. And so any the CDEs, they can approximate functions of this form over some subset. So K is a compact subset of the whole space CO1. So you don't really need to care about compact. It's just a necessary requirement for you to be able to approximate it. So these are the kind of functions that we can approximate. It's fairly general, right? It's you get a full continuous function of your path, and then just an integral along your path. So you can do quite a lot with this. And so if the matrices A1 to ADX are also diagonal, which is often the case for state space models, then it's a weaker model. We don't get quite as much expressivity, but we get functional of the following form, which are strictly weaker than what we have above. But at least we don't need essentially these two conditions on the top. So by taking diagonal, you get a weaker model, but actually you can just, it turns out that you can just chain diagonal models and be fine. Okay, so one other nice thing is that, okay, if I take again a compact subset of X, so X we can think as my like space of the space of sequences I care about, and then just take some subset of it that's nice enough to work with, then any functional um, of the form shown previously, so any functional of this form, it turns out that you can like sample a random CDE, linear CDE, which we get through Z. So Z of t is just a linear CDE with the A, so the A matrices and the B matrices and even the initial state generated randomly from Gaussians, so super easy. So it turns out that with high probability these will be close enough, or you'll be able to approximate f with these simply by taking an inner product with some vector v. That's sort of what it says. So if epsilon is small enough, okay, take large enough n, so n would be the size of your state. Then with high probability, take a random model, choose v, like basically only optimize over v, and you can get arbitrarily close to your functional f. Sorry. So this is nice because it means that take a high enough state and you don't even need to optimize like the A and B and so on. Only optimize the V, a single vector. So it might feel like a bit like either some kind of kernel transform or maybe a reservoir computer that's exactly that. But this is it's basically the same thing. But yeah, it's basically a reservoir, and the implication, they show a nice experiment in the paper that where okay, the Mamba needs some time to optimize, whereas this model, like they actually do this thing here and they get a good error. But of course, you might need quite a large state. So we can sort of combine two things here. So first, these random linear control differential equations can approximate any f with high probability as simply a linear product with some vector v. And v is the only thing that you need to train here. So it's pretty much exactly the same setup as in reservoir computing, which now we might want to look more into because I found this quite intriguing. And we also have that z of t, the signature transform, it only depends linearly on s of x. So really the signature is like the right features for path-to-path transform or just dealing with paths in general. Okay, so speaking of path-to-path learning, so we've talked about learning a function from a path to the real numbers. So let's say just like a classification a classifier, for example. Maybe we'll just take a path and transform it into another path. They have this small result here that says, okay, if I have a map G that takes a path and some time t and give me a real number, okay, this is actually equivalent to have a map from a path to a path in a sense. They say that G can be again approximated arbitrarily well if I first take a linear CDE and then map a neural network on top of that. And so if you have to do path-to-path transform, you just need a linear control differential equation, like let's say Mamba, then another MLP on top of that, and you're good. You're good in the sense that the whole class of functions here you can approximate. Maybe not the whole class, but most of them. So conclusions, but then I have the papers on hand. We can look at them closer. So we have a rigorous theory of the expressive power of state space models. This is very nice. We know exactly now, okay, Mamba can approximate functions of this type given enough size. Diagonal SSMs are a bit weaker, but just by chaining or let's say stacking diagonal SSMs, we increase the expressive power. So specifically, if you like stack k diagonal SSMs, you essentially get the power of k levels of the signature. So layer 1, 2, and for k. Okay, we have this randomized LCDs. These look essentially like a kernel version of SSMs, and in fact, a lot of the proof in that paper they hinge on basically just doing kernel reproducing kernel Hilbert space, so kernel methods. To me, might be interesting because might mean that we can get like some kind of NTK result where um, if you just increase the size of the system, it's not even like I think basically you have that result that you don't even need to train anymore. You're very close to your solution already. Um, Another thing which is so while browsing, so of course Patrick Kidger has been doing a lot of this stuff, and so he has this nice library for computing the signature transform, and he also has a paper about using the signatures not just like as a generic feature for your neural networks, but as a part, like a layer within your network. So that's I think let me yeah. So this paper here, it's very short, so you might want to take a look at it. Um, but I think this might be maybe a better introduction to the signature transform because they show some small examples, and they also show how they use it for some kind of stochastic process, so showing that you don't really need these very nice paths, even some very noisy systems you can work with. Okay, so that's what I had for now. Um, Questions? No questions? So how practical are
For
they to
the
compute in general? Sorry. Okay, I'll answer the first question, then yours. So how practical is the signature transform to compute in general? I mean, for arbitrary paths, you need to compute like all these integrals. Uh, I would assume that gets expensive really quick, like simply because okay, first of d squared and d cubed. So obviously there's a limit to how much we can compute. Um, though this paper talks a little bit about like choosing which terms you compute. And I think then it depends on the path. So if for piecewise constants or like simple paths, these integrals are really super easy to compute. So you don't need to have a full like integral solver. If you do, then okay, that's probably going to get more expensive. So I think usually you want to keep your path such that the integrals you can compute them exactly. But I think then the main bottleneck I think would be just that you cannot compute all the terms because you don't have enough memory. Okay, So Nev, you wanted to ask something? Okay, so maybe was that the same question? Maybe. No worries. Any other questions? I think we'll link this one previously, but let me link both of these. Okay. Um, yeah, I don't know. I think we can look at the, if I can find it. It's above. Yeah, so there we go. So for example, this is an experiment they showed comparing the so S5 um, with one or two like chains of S5. Same thing for Mamba, and then um, like their random linear CDE. And you can see that okay, the S5 oops does not do great here. Mamba does a little bit, but struggles, whereas the linear CDE was it's basically a kernel method at this point, so probably it has a lot more parameters. It's fairly good, and okay, in this case, um, Mamba can recover it. In this case, not. Although I'm not sure even what they're. All right, I think they're computing volumes and areas here. So small examples, but I thought it was fairly cool. Okay, so no more questions? You're sure? So how well would signatures work for embedding spaces? I mean, in essence, they already are an embedding. So, so I would assume they would work well if, at least for certain kinds of problems, definitely, because they already are an embedding. Like you, I think, yeah, here in this paper they show how you can like go from the signature transform to recover the path as a small example. Yeah, here. So for example, they had like path describing digits, and they computed the signature and then used the signature to recover the paths, and that works pretty well. So like okay, it seems to be that it's trivially an embedding. Um, Image features. What do you mean by image features for time series here?
Um, I'm thinking in the same sense as we use for images, we take features somewhere in the middle of a network. We take those features and we embed them in a space, and we can use that for a lot of different things. Just even for simple like clustering, disambiguating. If it is disambiguated, we can then use those. I'm specifically thinking of an example in audio. So something like where Mulan is embedding both text and audio. Those audios are streams, they're time series streams. If I was taking those and I was making signatures out of those audio streams and putting them in a space somehow, embedding them in embedding those signatures, could I then downstream use that embedded signature space for guiding other networks, for using to analyze or for synthesis? Does that make more sense? What I'm trying to say
Yeah,
there?
I mean, to me, yes, obviously. Like it is provably an embedding that like completely describes your data, only assuming that it's sequential. So yes, I think it would work. What you might lose out on is that okay, it's like a very general transform. So like you need to compute all those terms. So let's say you have like a high embedding, or your base dimension like is very high. Let's say 4096. Okay, even computing the first signature terms, that's 4000 right off the bat. Then okay, the second order you need 4000 squared. So it's it it's a powerful representation, but it's not necessarily a space efficient representation. But maybe some, I think there are some techniques for, I think this paper seems to have, okay, don't compute all of them, compute those you care. So yeah, practical limitations, but yeah, I would expect that it should work pretty well for audio and stuff. Okay, are we done here? Okay, looks like it. So um, if you want to discuss more, we can discuss in the math reading group. Otherwise, I think we can end it now. So I don't know exactly when the next one is going to be, but I think it might be time to talk about reservoir computing. That would be like a nice follow-up on this. But I'll make the announcement as always. So anyway, thanks everyone for coming, and see you next time.